Chapter 16, Equilibrium. This chapter deals with reactions that do not occur in one direction. One of the underlying ideas in this chapter is what's known as the collision model. It relates back to my discussion, my introduction to the subject of chemistry, probably on the first day of class. I remember all of you laughed when I explained to you that chemistry is the study of balls. And I wanted you to think of the elements as balls and the compounds that they compose of as balls. And that picture helps in this instance because reactions occur because the balls bump into each other. This capital M here, where it says M versus reaction events right here, this capital M refers to the concentration. How many balls do we have bouncing into one another? The second thing it takes into account is the temperature. Remember that temperature is not necessarily how hot or cold something is, but it refers to the average kinetic energy of the particles in a system. So if we have more particles or more balls, if they're hot, if they have a high temperature, then they're going to be bumping into one another more frequently. This is going to affect their condition. Some other conditions that affect our reaction rates are activation energy and catalysts. Activation energy. If more is required, then it's an endothermic reaction because it's going to absorb energy. If it gives off energy and less is required for the products, it's a exothermic reaction, gives off energy. All right, chemical equilibrium does not mean that these are the same. Chemical equilibrium refers to a dynamic state in which the forward reaction is equal to the reverse reaction. You might have remembered in the chapter on acids and bases that I introduced the two-faced arrow indicating a reversible reaction. And when we have equilibrium, the two arrows have equal length. If a reaction favors the forward reaction, the arrow pointing towards the products will be bigger than the arrow pointing away from the products. And the reverse is true if it favors the reverse reaction. These brackets here, these brackets refer to the concentration, right? The concentration of the products and reactants. We'll assume they're constant. And constant doesn't mean they're equal. And like I mentioned before, most of these, because it's based off the collision model, depend on two things: the concentration and the temperature. An important thing also to note, when we're at equilibrium, the forward reaction is equal to the reverse reaction. An important thing, when you understand the law of chemical equilibrium, we do not include anything that is a solid or a liquid. We're only referring to particles that are aqueous or in the gaseous state. The equilibrium constant. All right, now here comes the time for some math, okay? So let me bring over my doodler here. All right, the equilibrium constant, KEQ. KEQ looks like this. KEQ for equilibrium constant is equal to, it's always products over reactant, the concentration of the products I'm going to put a P here. This P refers to any of the coefficients. You're going to see how this comes into play if we have multiple compounds taking place. And then over here, it's over the reactants. And we're going to put an R here for reactant. Let's expand on this model a little bit more. Suppose we have, and also remember this does not include anything that's a solid or a liquid, aqueous and gas only. So suppose we have this equation. We have this equation says lowercase a element or compound A, lowercase b, element or compound B, and we have our reversible reaction here, and then we have, it produces compound C, and also compound, we'll call it D here. So if we were to calculate, now recall that these numbers here, these lowercase numbers here, are numbers that represent coefficients. These are our coefficients in our balanced chemical equation. I'm going to underline these so you understand these right here are our coefficients. So now if we wanted to calculate our K EQ for this equation, it would look something like this. We would do the products, the product of the products. So the concentration of compound C raised to the C power, this is for my coefficient power, multiplied by the concentration of the D raised to the D power. And this is all going to get divided by the concentration of the reactants. So over here we have A multiplied by the concentration of B. These are multiplied. And once again, I'm going to put this right here. And just as a note, all of these represent coefficients. This is how I would calculate my equilibrium constant. Let me put this aside for a minute and go back to my presentation here. One last note as we wrap up this discussion. There's two types of equilibrium. Homogeneous equilibria, where all the substances are in the same state of matter, and heterogeneous equilibria, where we have one substance that's say a solid, and another one that's a gas, and another one that's aqueous. All right, and don't forget, you never use solid or liquids to calculate your equilibrium constant.